All right, thank you, everyone. So this paper that we're presenting, it's called The Pros and Cons of Airfoil Optimization. And I'm actually really happy to be able to present this today because it's become something of a required reading for anyone in aerospace design, airplanes, rockets, optimization, which is something I think that most of us can relate to in some form or another. It was published actually quite a long time ago, in '98, by someone in our department, Mark Drela. And it was actually published in the form of almost a blog post tone. It's become a bit of a technical note that everyone kind of goes through when they enter this field. So let's motivate this a little bit. All right, so we're in the business of designing air vehicles, airplanes, rockets, the like. And most people have an intuitive understanding that the performance of a vehicle like that depends on the aerodynamics. But it's not always clear just how important that is here. It's really a first order effect. This is what we call the Breguet range equation here. It shows the range of an aircraft as a function of basically the three main disciplines that we look at when we design it. And we see that aerodynamics here is basically a straight multiplier on that. So you do a couple percent better in aerodynamics, and that very directly translates into better range, lower cost, lower emissions, all the things we care about. So a little bit of benefit there brings a huge payoff in terms of the actual real-world outcome. So some background here. All right, so if we're trying to talk about the aerodynamics analysis that we might do, in general, if we're trying to do that on a three-dimensional state, that's very computationally expensive. We're talking thousands of computer hours on a single design. So that's way too slow to iterate on new designs that we might be considering. To simplify this, we do something that is common in many computational disciplines. We take our problem, we break it up, and then we add structure to each part, which makes assumptions that speed that process up. In practice, what this means is that we split our geometry. So if we have an airplane here, we split it into the lifting surfaces in red here, and then non-lifting surfaces in blue here, and then we can use some different physics rules on each part to try to simplify the physics that are happening here. In general, these lifting surfaces here, these dominate the aerodynamic forces. So in a first order analysis, we usually focus most of our effort there. So there's some key insights here when we're looking at this 3D wing here. So we can make this problem even a bit simpler, and that's by observing that the airflow around one of these wings is typically almost two-dimensional. There's not much in or out of the page here. So what we do typically, if we're going to do a fast aerodynamics method, is that we treat this wing as a stack of 2D airfoils, these slices. And we'll analyze each of these airfoils in 2 dimensions, and then we'll integrate the properties across that wing. And then there's some tricks that we can do afterwards to capture those 3-dimensional effects that we missed. And that's a very quick method that reduces the number of degrees of freedom in our problem. So here's the main takeaway. If we can design better airfoils, these 2D slices, we can directly design better wings, better airplanes, and get better outcomes. All right, so let's talk a little bit about what this 2D analysis looks like in some of the prior work going into this. So a lot of the prior work by the same author gave us 2 key advances. One is very fast airfoil analysis. We're talking 1,000x faster than a general solution, which we would call RAND-CFD, with about the same accuracy. And the short answer of how that works is that instead of discretizing the entire 3D domain, we only discretize on the surface of that airfoil. So we're going from a 2D problem to almost a 1D problem. The other major advance that this author gave us is gradient information. So if we look at a typical aerodynamics analysis, we put in the airfoil shape that we care about, we run it through our numbers, and we get out lift and the drag. Those are the 2 things we care about. With modern methods, we get the same 2 things, but we get something else. And that's how the lift and drag change with respect to any individual change in that shape that we could make. And so that tells you not only how your design did, but also how you could improve that design. And the best part is that we get that at basically no extra computational cost. So that's really revolutionary. And it means that this is suitable for gradient-based shape optimization. So here's the natural question here. Can we actually do this? Can we design better airfoils by using these new analysis tools for computational optimization? And I should say that this paper is really coming at a seminal time when optimization and analysis are really becoming pervasive everywhere in the aerospace industry. So this paper presents a case study, and this is airfoil design for this airplane called MIT Daedalus. So this airplane here is a human-powered airplane. That means there's someone inside there pedaling it. That holds the world record for distance. It's actually unbroken 30 years later, which is pretty cool. It's very lightweight. So for context, this airplane has a longer wingspan than a 737, but it weighs less than a large dog. So what that means is that it's very low flight speed, only about 15 miles an hour or so. And that causes some very unique and delicate viscous aerodynamic effects that are pretty unintuitive to design around. And so the question here is, can optimization help? What was actually flown on this airplane here, you see, is this DAE-11 airfoil. That's what makes up this main wing section. And so we're asking, can a computer beat that? So if we want to answer that, we need to precisely quantify our problem. We need to take this abstract notion of better and put some numbers to it. So that means that we need three parts here: an objective function, a variable, and constraints. So the objective function is the thing that we're trying to optimize on. For this problem, we pick drag. So we're trying to minimize the drag of that airfoil. The things that we're letting ourselves change are basically the shape of this airfoil. And we look at how the outcome changes if we have 10, 20, 40 variables, more design flexibility that we're giving the optimizer. And finally, the most important part, the constraints. These are how we limit what designs are allowable. The most important one here is that the wing should make lift. So a wing that has low drag but doesn't make lift isn't particularly useful. And then there's some other ones that we add in for practicality. So the wing shouldn't twist itself apart, the wing should be manufacturable, et cetera, et cetera. So how did we do? So the takeaway is that optimization achieves a substantial drag reduction. That's pretty cool. On the left here, we've got the manually sculpted airfoil designed by an expert by hand. On the right, we've got the computer-designed airfoil, the optimized airfoil here. And if we look at the drag coefficient here at that target lift coefficient, and we see that we got basically a 16% drag reduction. So that's huge. That means that we really got a benefit and that we can get some range back. But unfortunately, this isn't quite the whole story here. So if you remember, our optimization goal here was to minimize the drag at that lift coefficient of 1.25. And the optimizer has done exactly that, but at the cost of increased drag basically everywhere else. So this plot here, we're looking at, it's really the drag here that's a function of the lift. So at some given lift value, how much drag are we going to get? The red line is the original design, the expert sculpted one. The blue line is what the optimizer gave us. And clearly it's trying to do something kind of weird here where it gives us that peaky performance. So the question here is, okay, so it did what we asked. Is that a problem? And unfortunately, yes, it is. And the reason is that the CL of this airplane is going to vary naturally in flight from about 1 to 1.5 or so. And so as we use more shape variables, we get this peak that becomes narrower and narrower. And so in flight, this optimized airfoil is actually going to have, on average, more drag than the original. This is what we call brittle performance. It means that it's very sensitive to exactly what you asked. So let's ask ourselves, what went wrong here? So the optimizer gave us the right answer. It solved our problem, but we asked it the wrong problem. So the question is, can we formulate this maybe in a better way, rephrase what we want? So on the original problem, we said minimize the drag at this lift coefficient. What if we ask, how about if we minimize the drag averaged over the upper and lower bounds of that range that we care about? Now what happens? Well, we get something kind of predictable here. So now it's optimizing with this peaky optimization at 2 points here. And so one of the interesting things here is that if you look at the light blue line, there are 20 shape variables there. On the dark blue line, there are 60. And so we see that as we give the optimizer more flexibility, it actually gets worse. It becomes even more peaky. And so that's a bit counterintuitive. The question here is, all right, so we got some benefit by looking at 2 points. What if we had more? Will that eventually solve our problem? So let's look at what happens if we do 6-point optimization here. So looking at 6 different lift coefficients and kind of doing a weighted average over how it does at all those points. And that actually starts to get us to something kind of interesting. We'll note that this blue line here is still kind of wiggly. It's going back and forth. And what that suggests to us is that this aerodynamic performance is still kind of delicate. There's some sensitive flow features that we may or may not actually be able to get in practice. But I should highlight that this drag reduction is still probably real. That's all of this shaded purple area here. That's a real reduction in something we might see in flight. The takeaway here is that for smooth optimization, we need to look at about the same number of points that we have shape variables, roughly the same order of magnitude. Otherwise, we're going to get some really strange peaky results. All right, so we focused on the performance of these airfoils that we looked at, but let's look at the actual geometry themselves, the shape that we got out of the optimizer. So to remind you guys, this is the original airfoil in red here. This is the DAE11, the expert design one. If we look at the one-point optimized airfoil, there's some unique things that have happened with the shape here. The most obvious ones are probably the concavity in some of the parts of this airfoil. And the question here is this a problem or not? It turns out that it actually is. And the reason is that because these human-powered airfoils are so lightweight, the way we manufacture them is basically by shrink wrapping them in Mylar. So if you imagine trying to shrink wrap a concave shape, it's going to create a little bubble there. You can't really manufacture it very well. So this may or may not be achievable in practice. The other unique thing, and this is not as obvious on the one-point design, but as you see as we progress, it'll become more obvious. There's a bump here that's developed in the top surface here. So what if we go to the two-point optimized airfoil here? All right, so same kind of basic idea, but now we see something kind of curious happening, which is that we went from one bump to 2 bumps. So this is interesting. Why is this happening? Let's see if we can go to the 6-point airfoil, and I bet you can kind of guess what's going to happen there. We're going to get 6 bumps, exactly on the top surface of the airfoil. So this is really interesting. As we go to more degrees of freedom, we're getting more tiny geometric features. So let's talk about why that happens. It's really curious that we're getting this. And the reason is basically that as the airflow goes over the top of this airfoil, it's starting out laminar and nice and smooth at the beginning. At some point, it's going to trip to turbulent and become a chaotic mixing flow. And the way it's going to do that is by forming a little laminar separation bubble. That's a little bubble of air on the top of the airfoil. And what the optimizer is doing is it's cutting a hole in the airfoil to exactly fit that bubble, right at the lift coefficients that we asked it to do. And that way, the outer airflow isn't actually seeing that bubble, which would normally cost us a drag penalty. So we've got 6 points here, one for each of our lift coefficients. But in reality, this isn't something that we can actually make. It's too tiny to be manufacturable, and it's also too sensitive to the exact values that we picked. All right, so let's tie this all together. The paper is called The Pros and Cons of Airfoil Optimization. So let's kind of lift those out of the paper. So the benefits are that optimization will tell you the directions of improvement when your intuition is exhausted. So if you don't know where to go, the optimizer can tell you what might bring a benefit. The second thing is that if you've got an unusual problem, like a human-powered airfoil, it can answer that problem for you as long as you can precisely quantify that problem. And then the last benefit is that it'll actually give you the right answer most of the time, but only to the exact question that you ask. So you have to ask it the right thing. The cons are that even for an expert in this, it's very, very difficult to pose the right problem on the first try. There's no way that we could have really predicted that the optimizer would be manipulating these tiny little bumps before looking at the result. So what that means is that instead of iterating on the design, you're still iterating, but you're iterating on the problem. So it's not quite this push-button approach that many people in the 1990s thought that it would someday be. The other thing is that optimization, especially as you give the optimizer more flexibility, gives you this undesirable local optimization, which isn't really useful in practice. So one of my favorite quotes in the paper is it talks about the almost devious cleverness of an optimizer armed with many shape variables. And so it's almost an adversarial task where you're fighting the optimizer to pose the right problem and constrain it from doing these undesirable things. And so it manipulates this geometry at these tiny scales in a way that might not actually be useful. So to summarize kind of the impact of this paper, so in the 1990s, as I said, there was a lot of optimism about optimization. There was hope that this would be kind of a push-button solution that would eliminate the need for expert-guided design. But in practice, that's not really proven to be the case in the 20 years since. And so because of this paper, most optimization studies on real-world airplanes, rockets, airfoils now look at many, many points or think very carefully before giving the optimizer total latitude over exactly what to do, because you'll find these effects. And although it's obvious in this case, if you design a full airplane, it might not be obvious until you actually go fly it and realize that the off-design performance isn't what you thought it would be. So thank you very much. If there are any questions, I'm happy to take them.
Nice presentation. I had a question about optimization itself. So how was the geometry parameterized? Was it starting with the expertly defined geometry? The second part is what optimization methods were used?
Yeah, that's a great question. So I'll get back to the shape formulation here. So there are a couple of different ways. One is if we have a good guess about the airfoil shape, we'll start with that, and then we'll add Bernstein polynomials or Legendre polynomials of some degree with different mode numbers to adjust the shape of that. We can also not start from an initial design, and there's some kind of candidate parameterizations. The long and short of it is that the parameterization doesn't actually matter that much. Once you get above about 20 or 30 shape variables, you can capture most of the reasonable space of airfoils with only a couple degrees of freedom difference between methods. And then to your other question about the method itself, so anytime you're looking at high dimensional optimization, which 20 maybe not quite high dimensional, but if you look at a whole airplane, that's very high dimensional. You want to use gradient-based optimization, just because the gradient-free stuff doesn't scale very well with respect to the number of input variables that you're optimizing over. So what we do here is it's a stabilized Newton approach with a line search in the middle, kind of a standard off-the-shelf method with an exact hessian because it's not very many degrees of freedom.
Spencer, you want to
Yeah, thank you. That was a great talk. Great question. Yeah, great talk. I'm not familiar with this whatsoever, so you talked through it really well. So one quick clarification question. I have a couple of questions. So the novelty of this, you said, was that he designed the 2D integration method, which enabled this optimization. And so this optimization, so the method itself is new, plus the optimization we're seeing, that's something that couldn't have been done before. Is that true?
Yeah, so the fast analysis is basically just increasing the speed at which this could be done. You could do this with traditional methods, but it'd take you about 1,000 times longer. So the iteration process, if you need a human in the loop to see was this the right problem to ask, that just slows it down massively. And then the gradient information is nice because it actually cuts down the optimization runtime by the number of degrees of freedom. So if you get the gradient for free, so how these values change with respect to all 40 things, and you get that for free, you no longer need to run each individual perturbation to build up that gradient. So this makes you about 1,000 times faster, this makes you about 40 times faster. Put together, in theory it's possible without these, but it's impractical. Yeah.
That makes sense. That's a good answer. And so, say it's slide 15, you have the lift versus drag curves. I assume these are, I guess, how are these plots made? Are they locus of points of different designs or different,
It's a great question. Yeah, so there are locus of different angles of the airfoil. So you start it at 0 and you kind of tip it up. So normally kind of the way that one might think about this is you plot that angle on the x-axis and the lift or the drag on the y-axis. But it turns out that the actual angle is a bit inconsequential because you can always just twist the wing to get it to the angle you want. So what we do is we sweep over that entire angle and then we plot the two things that we actually care about, which are the forces, because the angle itself is pretty easy to manipulate just by building it in.
Thank you.
Yeah, my question is about, so this is a particular example for not a very high Reynolds number, right?
Yeah.
And then you talked about the laminar separation bubble effect.
Mm-hmm.
That's something that's only really prevalent at lower Reynolds numbers,
That's a
right?
good point.
So I wonder what happens to this whole analysis when you do it for a high Reynolds number situation.
Yeah, that's a great question. So as you said, as you get to higher Reynolds numbers, that laminar separation bubble becomes smaller. You could trip the flow at the beginning. This is an illustrative example. There's another example in the paper about a high-speed flow, which is a transonic airfoil design. And one of the things that you'll see is, so transonic airfoil design is dominated by the shock formation. You really want to minimize that or at least delay that. And so they show that even in that case, you'll get tiny geometric manipulations to move that shock wave forward and backwards in a way that, again, is not really manufacturable. So although this effect is most prominent at slow speed, at high speed there are different effects that you'll get that still cause a similar phenomenon, but from different physical mechanisms.
Okay, but there's not like a Reynolds number range where this is actually a good approach, or a good approach to sort of go offline. Because you you went to Transonic, which is
Yeah.
obviously in the paper then, but it's
Right.
more like the upper end again.
Right, yeah, so there is probably, so if you decrease the number of degrees of freedom, so you didn't let the optimizer work at that small scale, you could probably fly these designs. And in fact, the 6-point design is a reasonable approach if you could build it, which is the one question about can you actually do that shrink wrap on the concavity. So, you know, that's not, this paper is a bit of a, it's meant to pump the brakes on optimization, but it's not meant to kill it. So there definitely are places in optimization where it's exceptionally useful. Most of my work is in aircraft design optimization. So, you know, in the 20 years since, we still do optimization because it's still useful. This is just mostly meant to caveat that you can't just push the button and then go build exactly what comes out. There needs to be a human in the loop sanity check process afterwards to just make sure that you're not getting into one of these weird cases.